All right, so what we'd like to do now is we'd like to move from one dimension to two dimensions, but do this with kinematics. So we'd like to look at kinematics in two dimensions, take the previous two discussions and put them together, basically. So, how does that work? So what we'd end up doing would be with uniform motion, which we said was when a particle moves in a straight line at constant speed. So we'd like to look at moving in a straight line at a constant speed. Okay, so what does that end up being? Well, in this case it's nice. We can use the average velocity because the average velocity and the instantaneous velocity are the same thing. And we want to put this together by saying we've got our position at some time t is equal to our initial position plus our velocity, which has a hat, and times t. So these are all vectors, right? So we have a vector velocity, and that's in two dimensions. That's why it has the arrow. We have the current time, and we have the initial position. And we can put all these together, and as long as there's no acceleration, and find the current position. Now this looks really bad. It's all these vectors and stuff. But we don't really have to do that. We can break our vectors up into two, right? So our technique is to break our x and y components up into different things. So we have our x component, which would be x of t, is equal to the initial x position plus the velocity in the x direction times time, and the y. There's no hat there. Y of t is equal to y naught plus vyt. And this works as long as our position is the sum of our x and y components, or it's the vector with x and y components here. Our velocity is a constant, so no t, vx vt, vy, excuse me, and so on. Notice the only way these things are connected are through the time. We only connect through the time. Everything else, not our problem. All right. So then we go on and we say we want to look at uniform motion. All right. We're looking at uniform motion. What does this look like? Well, let's just look at the initial position. Right. So we'll draw an arrow. This is our R0, initial position. Another way to say that is it's our position at t equals 0. And that's our position right there. Okay, so that's just drawing that one vector. And what we're going to do is, as we change our time, we're going to keep going in a straight line, so at a constant speed. So maybe our next position would be this one. That would be r at 1 second. Then our next position, which should have the same distance, would be r at 2 seconds, right? Go the same distance in the same amount of time, and it has to be all in a straight line, sort of like this. Okay, remember, this is an xy coordinate system, so this has a slope of that v, right? This guy here. So we could figure out the angle here by saying that the angle of that is equal to vy over vx. Not this, this. Okay. So that's more or less what we have for uniform motion. When something's going in a straight line, like say this ball. Then with uniform motion, the distances between the objects stay the same for the same amount of time, the same duration of the process. And there's a slope that's equal to the velocity of in this xy plane. It's in the xy plane only. All right? So that's the basics of uniform motion. Next, an example, then some more stuff on acceleration, how acceleration changes velocity. That'll be quick. Then we'll talk about parabolic motion. Bye now.